Throughout all our discussions of Markov chains and Markov processes, we've been primarily concerned with finite dimensional distributions, meaning joint distributions of the process at any finite collection of times. But among those, we might be interested in the good old-fashioned question of the distribution at each particular time. If we start our process canonically in some point mass distribution, then we would expect that after a step of our Markov chain, the distribution is no longer a point mass. If the distribution is always a point mass, then it's not really a random process at all. It's just an actual deterministic process between a bunch of points. On the flip side, is it possible to start our Markov process in some distribution so that as the Markov process proceeds, the distribution of xt at each time doesn't change, but is stationary? That's the question that we'll answer right now, at least for finite state discrete time chains. Here's our definition. First of all, if xt is any Markov process with homogeneous time, transition semigroup qt, and we have initial distribution mu for the process, then of course we can compute the distribution of xt for any positive t. That law is calculated using this notation, law of xt dy, by doing the integral over the initial distribution dx qt of x dy. That's how our transition kernel is defined. Well, what we're asking about is there a measure mu, which we'll call an invariant distribution or a stationary distribution, if this is always equal to mu for any time t? Before we answer the question of whether it exists in some cases, let's note that if such a distribution exists, so that starting in distribution mu, you're in distribution mu for all time later, remembering all of our characterizations of the Markov property, that will mean that if we start our Markov chain somewhere and eventually get to the distribution mu at some time t0, which may not be at the beginning, then of course the law of mu t for t later will be the integral of that distribution at time t0, which is mu, integrated against the transition kernel from time t0 up to t, which is in this homogeneous setting qt minus t0 of x dy. But this is some positive time, and so by our assumption here, that will also equal mu. So if there is a stationary distribution, if we ever reach it starting anywhere, we will stay in it forever afterward. Now in the discrete time setting, this condition of stationarity only needs to be checked for one step of the transition. Indeed, if we look at the law of the process at step n plus 1, then that's, as we've been writing, the integral of the law of the process at step n being t0 from this example here, integrated against the one-step transition kernel. And so we can proceed inductively. If we've shown that the law of the process at time n is mu, then this is the integral of mu of dx, q of x dy. And that, by our assumption of the one-step transition kernel behaving stationarily, is mu of dy. And so by strong induction, if you like, we get that the law of xn is invariant. After we reach distribution mu, we stay in that distribution forever afterward. And just to be clear, what this condition means in the discrete state space, discrete time setting, is that the probability measure mu, which we'll usually also use to denote its probability mass function, mu of j, is equal to the sum over all states I of mu of I q of ij. As we've noted before in terms of matrix multiplication, this is multiplication on the left by a row vector, as opposed to multiplication on the right by a column vector. We compute the transformation of the law of the process by multiplying row vectors on the left of the transition matrix, and we get the action of the transition operator on functions of the process by multiplying on the right by column vectors. So, focusing for now on this discrete space and time setting, let's try to answer the question of whether we can find such an invariant distribution. Let's write things again in terms of matrices explicitly, and so let's actually restrict to the finite state space setting. Suppose that these states are labeled 1 through d. Then we can think of our probability distribution mu that we're looking for as a vector, which I'll call v right now, by putting its probability mass function into the entries of this, let's say, column vector. That's got to be a probability vector, so all of these are non-negative and they sum up to 1. And so with this setting, if we then use capital P to denote the actual matrix associated to this kernel, this is a D by D matrix, then what this condition here says is that the row vector V transpose is equal to V transpose times P. Or in other words, V transpose times the identity minus P is equal to the 0 vector. So, in other words, what we're asking for is whether the matrix I minus P has anything in its left null space. And the answer to that is going to be always yes, because P is a stochastic matrix. Its rows sum to 1, which can be written in matrix terms like this. If I take the matrix P and multiply it on the right by the vector, all of whose entries are 1, that exactly computes the vector of the row sums. But those have all got to be 1 as well. So that means that this 1 is in the right null space of P minus the identity. So that means that the rank of the matrix P minus I is not full. It's at most D minus 1. But the rank, which is more properly called column rank in this case, is the same as the row rank. That is, this is the same as the rank of P minus the identity transpose. And that tells us that this transpose matrix has something in its right null space, which means that P minus I has something in its left null space. That is, there exists a column vector W in RD such that P minus I transpose times W is equal to 0. And if I take transposes of both sides, that tells us that the row vector W transpose times P minus I equals the 0 vector, which is what we were hoping to find, right? Well, almost. That is what we were hoping to find, but this doesn't tell us what kind of vector this is. The condition here is not just that there's something in the left null space of I minus P, it's that there's a probability vector there. We would need to show that this W transpose here has non-negative entries. If it has non-negative entries, then it doesn't matter what the sum of them is because we can always rescale. As long as those entries are non-negative, and this is not the 0 vector, which is our supposition here anyway, then we could define V to be 1 over this non-zero sum of the entries applied to W, and then by linearity of matrix multiplication, we'll get that this vector is also in the left null space and is a probability vector. So the question before us is, can we modify this argument to show that we have something in the left null space that has all non-negative entries? And the answer to that question is yes, we can. And here's how we do it. We follow exactly the same steps that we just followed in order to produce a row vector W transpose that is in the left null space of the matrix P minus the identity. And now we're going to define a new vector, V, whose entries are the absolute values of the entries of W. And I claim that that vector is also in the left null space of P minus the identity. It is going to be the kind of vector that we need. Now, of course, that's not going to be true for any arbitrary matrix. This can't be just a linear algebra argument. We're going to have to use the probability somewhere. In other words, we're going to have to leverage the fact that P is a stochastic matrix here. And so here's the idea. The key estimate is that the jth entry of the vector V, which is the absolute value of the jth entry of the vector W, well, W is an invariant vector for P, so Wj is equal to this sum. And its absolute value is therefore less than or equal to the sum of the absolute values inside. Now the Pij's are all non-negative, and the absolute values of the Wi's are the Vi's. So that's sort of half of what we wanted to show. We wanted this to be equal to this, and what we've shown is that it's less than or equal to. Now, rather than trying to explicitly show that it's also greater than or equal to, what we're going to do is assume that's not the case. Assume there is some j so that this is a strict inequality, and derive from that a contradiction. So suppose that's the case. Suppose that this is not equal the way we want it to be. That means, as I just said, that there is some j for which Vj is strictly less than the sum over I of Vi Pij. And from that, what we can derive is that the sum of the entries of V is strictly less than the sum over I and j of Vi Pij, just summing this over j. But now we can order that sum like this. Let's sum on the outside over I, Vi, and then the sum over j of Pij. Oh, but that inside sum is just 1. And so this says that the sum over I of Vi is strictly greater than the sum over j of Vj. That says this number is strictly greater than itself, which of course is a contradiction. And so that does show that this vector v is a positive entry vector which is invariant under left multiplying p. Since it's not the zero vector, that's the way we designed w, to be in the null space, not the zero vector, that means that we can normalize it and define our probability vector, as we stated, just using the linearity of matrix multiplication. That tells us that this vector mu satisfies mu transpose p is equal to v over that sum, which I'll denote as the L1 norm of v transpose times p. Of course, we can just take out the 1 over v1 norm from that linear operation of transpose, v transpose p, and that's 1 over the length of v1 in L1 norm v transpose by what we've proved here, which is equal to mu transpose as claimed. And so that concludes the proof that any finite state Markov chain has an invariant distribution. Now, by the way, this result that we've just proved is a version of what goes under the name Perron-Frobenius theorem. This is the easiest possible case. We've proved that any stochastic matrix satisfies this property. Thinking about it a little bit more, what we're actually showing here is that 1 is an eigenvalue for p. That's going to be true for any stochastic matrix because the constant vector of all 1s is an eigenvector with eigenvalue 1. And that eigenvector can be chosen to have all non-negative entries. It's also easy to check that for a stochastic matrix, 1 is the largest eigenvalue. And so the full Perron-Frobenius theorem says that if you have any matrix that has non-negative entries, then it will have a unique largest modulus eigenvalue. And in the eigenspace of that eigenvalue, you can find a vector with all non-negative entries. Now, there are even versions of that theorem which work in some infinite dimensional contexts, but we shouldn't be fooled into thinking that we can just generalize this result to infinite state, discrete time Markov chains, because it's just not true. Let's look at the one example that we spent a lot of time studying, simple random walk on the integer lattice. There we have our transition kernel given like this, and let's note that that transition kernel is actually a symmetric function of I and j. In other words, this matrix is symmetric. And what that means is that taking the transpose doesn't affect the transition kernel, and so multiplying on the left or the right by our vector will produce the same result when we track through. That's going to be handy here. So let's suppose that we could find an invariant distribution mu for this simple random walk transition kernel. Well, that means that for each j, mu of j is this sum here. But let's reverse j and I in this sum and write this as a multiplication on the right instead. This is the sum over I of q j I, mu of I. And that says that the function mu satisfies mu is q times mu on the full integer lattice, where q is, of course, the transition operator. Well, we've studied that recurrence relation in the last several lectures, and if this holds for all j and z, then we have a unique two-parameter family of solutions. We know that mu must have this form here. It's some generic affine function of the variable j. But that's going to present problems for us no matter what a and b are. Since this must be a probability distribution, mu of j must be non-negative for every j, we can't have any non-zero b here, because no matter what non-zero b we put here, there'll be some j, either positive or negative, that will eventually make this a negative number. So we can conclude that b must be 0, but that means that mu of j is just constant. Oh, but remember that mu is supposed to be a probability distribution, which means that this sum has to be 1, and there ain't no constant whose sum over the whole integer lattice is 1. And so we conclude that the simple random walk does not possess an invariant distribution. Now, if we loosen our conditions and allow for this measure mu to be an infinite measure, not a probability measure, then we do see that there is an invariant measure. If I take the counting measure on the integers, that is, the measure that has probability mass function 1 at each integer, then that, or any positive multiple of it, will be an invariant measure for this distribution. And in fact, it's again easy to see from our analysis here that that will be unique up to scale. So this is going to be an important observation. If we have an infinite discrete state space, we may not have an invariant distribution. But it turns out that aside from some obstructions that we'll note in a moment, we will typically have an invariant measure. Anyway, in the finite state space case, we've now shown that there always exists an invariant distribution, even if the chain is not irreducible. However, it may not be unique, and in fact, we'll find that's the case for non-irreducible chains. Typically, there'll be multiple different invariant distributions. But if we have a finite state space irreducible Markov chain, then there is always a unique invariant probability distribution. And in fact, we can write it quite explicitly. The probability mass of this invariant distribution at the state I is exactly the reciprocal of the expected return time to I, which will be strictly positive for each I. Now remember, last time we showed that in this setting, finite state space, irreducible Markov chain, these expected return times are all finite, and therefore this is a strictly positive number. So let's prove this nice little probabilistic theorem. We'll start by repeating more or less word for word the first step analysis that we did last time in showing that the return times had finite expectations. The expected value starting in state I of the passage time at j is the sum over all states k of qik times the expected value starting in state k of the passage time of the new chain appended with a state I at the beginning, and then the chain x continuing as before afterward. We'll write this first taking out the term k equals j, so that's qij times, well, in this case, when k is equal to j, that means that the next state here is j, and so since that's at time 1 for this process, the passage time is going to be 1. And then we have all of the other states, k not equal to j, qik of the expected value, starting in state k, of the passage time hitting j of the chain ix, and in this case, because x0 is equal to k, which is not equal to j, that means that this time inside here is exactly 1 plus the passage time of the original chain x. Now we can add up this qij with all of these 1 times qiks with k not equal to j. That gives the sum of all qiks for all k, which is just 1. And then for the other terms there, we just have qik times the expected value starting in k of the passage time at j. So we have this expression here. Now that equation there is going to be useful to us not only in this proof, but afterward as well in computing these expected passage times, as we'll see. But for now, we're going to use it like this. Suppose that mu is any invariant distribution. And remember, we've already proved that some invariant distribution exists. So choose one of those invariant distributions, mu. then from here we can get that if we sum up over all states I, the ith entry of mu times the expected passage time starting in state I of j, well, that quantity there can be written like this, and so we expand this sum like this. It's the sum of 1 times mu I, but of course mu is a probability distribution, so that is just 1, plus these terms here. And now I'm going to reorder that sum, first summing over k not equal to j, which means that I may as well pull out the expected passage time term. And then on the inside, I sum over I, mu I, q I k. But mu I is assumed to be an invariant distribution, which is exactly to say that that sum is equal to mu k for each k. Now what does that say? That says that this sum here is equal to 1 plus this sum here, which is the same sum again, just with the jth term removed. So if I subtract this from this, what I get is that the one remaining term, which is just mu j times the expected value starting in state j of the passage time at j, is equal to 1. Now that subtraction is allowed because this is finite. All of these terms are finite, as we proved in the last lecture. So, to summarize, what we've shown is that if mu is any invariant probability distribution, then it's given by this expression here, where these are non-infinite positive numbers. Since we already proved that there is some invariant distribution, this shows that there is a unique one, and it is given as we desired by the reciprocal of the expected return time of each state I. Now, one quick corollary that we get from that right away is something we didn't note before, which is that if you have a finite state irreducible chain, not only is there a unique invariant distribution, but it is strictly positive. These are finite numbers, and therefore the reciprocals are not zero. So the invariant distribution has all strictly positive masses at all states. Something else that we get, a piece of information about the expected return times that we didn't have before, is since, as we showed in the last lecture, that these are all finite, and of course strictly positive since we're taking reciprocals here, we now know from the fact that these mu's are a probability distribution that the sum over all states of the reciprocal of the expected return time to that state is equal to 1, which is kind of interesting. Now, before we close the book on these invariant distributions, let me just note that a very similar result holds for infinite state Markov chains. If you know that the Markov chain is irreducible, which in the infinite case is not enough to guarantee that it's recurrent, so we also must guarantee explicitly that they are recurrent, meaning that the return times are all finite with probability 1, then indeed any such chain will possess a unique up-to-scale invariant measure. Now, it could be a distribution. There are infinite state Markov chains that have invariant distributions, but some, like the simple random walk, do not. They do have an invariant measure, which will be strictly positive and unique up to an overall positive constant scaling factor. And we do have the tools to prove that, but I'm not going to take the time. I'm just going to note that you can express the unique up-to-scale invariant measure in similar terms to what we've done here, not necessarily in terms of reciprocals of expected return times, but in terms of expected number of visits to a state before it returns. But we'll save that for another course on Markov chains. Now, before we fully close the book on this discussion, let me note how the tools we developed in the proof of the last result actually allow us to efficiently calculate expected return times and, in fact, expected passage times in wide generality for finite state chains. This equation played a key role in our proof there, and in fact you can see that this is a recursion for these quantities. But we don't really need to think of it as a recursion. In fact, it's just going to be a linear algebra equation. If we denote the vector, which has for fixed j these as its entries, I ranging through the states, that is, uj is the vector whose ith entry is the expected passage time to j starting in state I, then what this equation here says is that the ith entry of uj is 1 plus the sum over all states k not equal to j of qik of the kth entry of that vector, uj. If we write that in vector notation, what it says is that the column vector uj is equal to, well, there's a 1 in each entry here, so this column vector of all 1s, plus a certain matrix times the column vector uj. What is that matrix? Well, it pretty much looks like the transition matrix for the Markov chain, except that this is not a sum over all states, but is a sum over all non-j states. In other words, this matrix Pj is the matrix whose ik entry is qik, the transition matrix entry, but zeroed out along the jth column. So what that says now is, subtracting this from that side there, what we get is that this vector of expected passage times can be computed as I minus that matrix Pj inverse applied to the constant vector of all 1s. Now, I haven't proved for you that this matrix actually is invertible, but in fact, that's going to follow by the uniqueness of invariant distributions that we proved already. And so this is a very simple computation that can be done now in finite dimensions quickly and easily on any computer algebra system, or by hand if you like that sort of thing. And if you'd like to see some of those computations explicitly working out the exact values of the expected passage times of a particular finite state Markov chain, you'll find many such examples in Driver's Notes.